thank everybody for taking time and coming down to warm up. We're going to be talking about fire. Our presenter today is Dr. Dipak Dulal. He comes to us from the University of Alabama at Birmingham. This is his first year, I believe.
Yes.
This was an interesting proposal because, not because it was cold today, but because of the idea of using mathematics, machine learning, and other kinds of models to be able to predict things which are happening more frequently in our lives in terms of climate change, fire, and fire emergencies. That perked my interest in this, and I hope it does for the rest of you as well. As always, I want to thank the committee members for helping me get this presentation here today for voting. Basically, it's Dr. Kathleen Wagner, Dr. Pamela Schuler, Dr. Matthew Haney, Dr. Chelsea Starr, and Dr. Brian Pasco. And I thank you for being here today, Brian. As always, I want to shout out to the support that we get for this lectureship from Academic Affairs in Dr. Lorenzo's office. Not only the financial support, but Melissa Brose there helps with the food, because if it was up to me, it wouldn't be as good as it is with her. She's very, very good at that. And Maddie, of course, from Sodexo sets this all up. I want to thank John Hauser and Comm Services, for Adam and Maragon for basically filming this and presenting it later. All of you, thanks for coming out, and hopefully this will warm us up a bit. So without further ado, I'll turn it over to you. Thank you.
Thank you, Dr. Mark Murray. Thank you for your introduction. I'm talking today about the exploring and analyzing behavior of wildland fire by machine learning. Definitely there is some math, but I wanted to exclude much math because that's most people don't like. Yeah, but I wanted to make more like audience oriented talks, but it's not possible 100%. And this work I have done during my PhD, final year of PhD. I did an internship from USDA Forest Service. It was the good research I did. Let's begin. This is the outline. There are a lot of things here. You see, you might think that it's a lot to complete, but I swear I'll complete within the time. And I'll start with the motivation. What motivates for this research? I put some data. This is the recent data from National Forest Protection Association. It's data from 2012 to 2025. And the left bar, here left Y level, we have the burn area in hectare. Like every year, how many area was burned due to the wildfires. You can see 2020, around 70 million hectare area was burned in only United States. It's not all over the world. If you look at all over the world, you can imagine just how much area was burned every year. And the data shows that 23 and 24, it seems a bit decreasing, but the overall like 13-year periods, the graph, it doesn't show it's decreasing. It's like on the flat, it's not decreasing much. And maybe you might know that recently, the California wildfire, the data is not included here. The 25 data might be up after that. And this is the one, and next data, the motivation here is the economic loss, how much money we are losing every year, right? This is the Joint Economic Committee from US Congress. They have published this one. The data is every year, it's around 893 billion, right? Money we are losing from the wildfire in the United States. That's only from real estate is the most highest one, 337 billion cost we are losing from real estate diminishes. And another exposure to the wildfire smoke, that's the second one. Third one, income loss from wildfire. These are the terrible loss we are doing every year. And what I'm thinking, I don't have a solution of this, right? But if I have some tiny things, research I can do to get the manage to help for this kind of loss, that would be great. Small, tiny, small, because it's huge. And let's begin with what is the objective of my research. This research based on the control fire data, right? Control fire, it's not the wildfire like California just faced. It's a control fire data, and from the data we have started with the data pre-processing, then investigate the correlation between the 10 Hz time series thermocouple temperatures. Thermocouple temperature is the device that extracts the temperature from the wildfire, and I'll talk more about that later. And next, turbulent kinetic energy. That's our main target data. That's computed from the sonic anemometer 3D wind speeds. During the wildfire, there is a wind speed from left, east to west, up to down, north to south. That data was collected from the sonic anemometers. We computed TK, that is physical term, I'm going to talk that. Find the correlation. Is there anything? We can find the combination between them. And next, estimate the turbulent kinetic energy. That's the key points to have a fire turbulence, to analyze the fire dynamics. Using the deep neural networks and diverse ensemble machine learning algorithm I have used. And the last, examine the precision and legitimacy of our project, our models. Now, this is the machine learning workflow. Right, I started with the data acquisition, how the data has been acquired, right? And then it's a data pre-processing. It's hectic work. We did a lot of work from the data preparation. That's a raw data we got, and data visualization, how it's going, and then exploratory analysis, like we did the linear and non-linear correlation between the predictors and target variables. Then we use the bunch of machine learning algorithm. We have used a lot of machine learning algorithm with trial and error, and did a lot of tuning. And we got 6 machine learning algorithm that is important to define. That is Gaussian processing, regressor, gradient boosting, k-nearest neighborhood, deep neural network, random forest regressor, and extreme gradient boosting. These are the machine learning algorithm, especially we have used to estimate the turbulent kinetic energy. Next, to ensure that our project, our algorithm, our machine learning algorithm, they are robust and effective, we tuned hyperparameters and regularization. There was some maths. We need to go to inside the algorithm, and we did some ups and downs using our mathematical insight, and to make the algorithm best, to get the best result. And to evaluate our result, we did the cross-validation, model evaluation, like using KD, kernel density estimation, RA square, that is the tools to determine accuracy test, mean square error, and mean absolute error. Then model comparison over the models, and the key finds. These are the workflow of our research. Now let's see how data has been produced. It was the experiment on the New Jersey. There is a place, New Jersey, New Lisbon on New Jersey. The USDA Forest Science Department has a private forest for the experimental purpose. That is called Silas Littered Experimental Forest. And they have done the experiment from March 2018 to June 2019. And they made the plots of area 100 square meter, 10 meter by 10 meter plot on the forest. They didn't change the landscape of the forest, just made the plot, and set up the instrumentation here. You can see the first figure. There are a lot of instrument. They are aluminum. The trusses are there, 4 trusses, A, B, C, and for each trusses there are sub trusses where the data collector machine were instrumented. Like you can see here, A1. Here is a A1 instrument, A2, A3. You can say the sub truss also. B1, B2, B3. Each 4 trusses, we have a lot of machines who are there, like a radiometer here, sonic anemometer. This is an infrared camera, and a lot of instrumentation has been here. And this is the total setup of instrument to collect the data. And this one is the during the fire, during the burning time, the instrumentation are there. The spectral high-speed pressure sensors here, sonic anemometers that extracts the wind speeds, and thermocouples here that extracts the temperature from the different height, from the 0, from the 5, these different height temperatures here. And yeah, that's why this is called prescribed fire data. Prescribed means fire is made by the human, and it is controlled fire. How the fire goes with different. Look at here, this ground, this ground are the fuel beds. This forest is the pine forest. There is a pine needles, some woody materials, and grass. They kept uniformly to the plot before igniting the fire. How the fire ignited? First of all, they take the 10-meter rope with some fuels, and they take the fire on the rope, entire rope, and they put the rope at once to the plot, and fire starts burning. And then all the machines starts to collect the data while they're burning the fire. That's how the data has been collected. This is after 6 minutes of burn. They have taken the one sample picture here. There are a lot of pictures, and these are the trusses. Here is some devices has been set up to collect the data. This one, and this is the infrared image from the sensor. They have taken infrared image. It is like you can see here, IR camera here. It takes the image. And I didn't talk about the 10 Hz data. It's a 10 Hz, not 1. 10 Hz means the data has been collected. It's a frequency. Every second, 10 data has been collected for every second. That's called 10 Hz data. And our focus. And we have, when I started the research, there are 5 terabyte data was sent to me what is the data you are focusing on. And our focus, we discussed a lot about, and we focused the 2 data. One, sonic anemometer wind speed data we took, and there is another thermocouple temperature data collected from the trusses B and C. There are 4 trusses, A, B, C, D. B and C are on the middle. And we got the data from 2 trusses, B and C. B has a 4 data collection center, B1, B2, B3, B4. C has also 4, C1, C2, C3, C4. We have actually 8 data sets. And the data set has wind speeds and temperature. Wind speeds are denoted by U. U is the variable east to west, meter per second wind speed. V, north to south wind speed. And this is a W, this is a up to down, that means vertical wind speeds. And another variable, sonic temperature, that is the temperature determined by a sound wave. Sound wave also creates the temperature, that is sonic temperature. And thermocouple, and this is the wind speed. And this one, another one, thermocouple temperature, T1, T2, T3 up to T7, they are collected from the different height. Look at it, 0 centimeter from the fuel bed, 5 centimeter, 10 centimeter, up to 100 centimeter, the device has been set up and data has been collected. These are the temperature data. And UVW are truncated. We did, the outliers are out, -50 to +50. This one, data classification, we classified the 3 types of data. There are huge data, we have to truncate it. First data, pre-burn. Before the burn, there is a set of data. During the burn and post-burn, after the burn. And we focused on the during the burn data, right? While it is burning, we focus on that burn. We truncated that with respect to the time. What time it started burn, when it ends, right? The fire scientists, they made some thresholds. And we did the perturbation. There are a lot of ups and downs on the wind. And we try to make some smoothing, right? Some smoothing there is. And the smoothing has been done perturbation. U prime is U minus the average of U. We have a U column, find the average of them and subtract from each value. That's the perturbation from U prime. Then turbulent kinetic energy, we computed it. This is the physical term, right? Turbulent, this is the very important term for fire analysis. One maybe British physicist, he discussed a lot about the turbulence theory in physics. And its formula for computing is 1/2 U prime square. This is the mathematical formula to compute the TKE. And that is our target variable. We want to estimate TKE by using the temperature. TKE is based on the wind speeds. But does temperature affect the TKE? That's our question for the research. And we use the TKE moving average. Right? TKE also has a lot of fluctuation. We want to make less fluctuation, right? So that the smooth data would be better to to use for the machine learning algorithm. So for that we did the moving average. This is the statistical term. Moving average, we did a 10-point moving average. We got the average of 10 points and subtracted from each value. That's moving from the average from the column. That is the TKE moving average we have. These are the T1, T2, T3, T5, T7. Up to sonic T, these are the predictor variable. We are training this. And this is our target variable. This is our response variable, TKEMA. And this is our time. Time starts from 3 p.m. Eastern time. And 30 second, 3 p.m. 25 minutes, 30 second. And 0, 1, 2 means every second there is a 10 data. This is the time series data we have. This is the ready-made data to go for the machine. Now let's go to the data visualization. After detailed data pre-processing, we got the data and we are looking for how data looks like. This is the data. You can see here U prime, W prime, V prime. These are the wind speeds. And we computed TKE, turbulent kinetic energy. These are the data you can see, and TKE only. The green one, you can see the green one is more smoother than the TKE. That's what we wanted. We are successfully make more smooth data for the TKE, and these others are the wind speeds. Wind speed is changing during the fire burn, right? It depends on the fuel bed also. Somewhere there are a lot of pine.
The fire makes a turbulence.
Yeah, a lot of turbulence. Somewhere the fuel bed is lower, not that much good, and turbulence is less. That's how it is. It looks like. Now next one, this one is the temperature. Thermocouple temperatures. These are the T1, T2 up to T7. It is collected from the different height of the fuel beds. From the ground, that means just above the fuel beds, 10 centimeter above T2, 20 centimeter above T3. When your height goes up, then how the temperature is changing, right? That is also determinant factor for fire turbulence. That's the data here. It starts from X coordinate is here, the time. 3 p.m. I didn't write the p.m. here, it's a long, that's why. It is 23 p.m. Eastern time, 25 minutes, 30 seconds. It starts collecting the data, go all the way up to 32 minutes. That means total 7 minutes take. Fire was burned there. And maybe this peaks is at the middle of the fire. When fire is burning a lot, the temperature is at the peak. This is starting. This is like fire is getting over. This is the turbulence, temperature turbulence during the fire burn. Now this is our machine learning model. Right? I think you don't like it. This is a bit math. This is the data set we have. We have to make all the data that is ready for the machine, because machine knows only math. Machine doesn't know anything. There's no math. That's why we have to make the data into the matrix format. Right? This is the data matrix D. It has X as the input variable. These inputs are our temperature data, T1, T2, T3 up to sonic. We have 8 feature data. That is for training purpose. We are training the machine, right? We are making the machine can learn something from our data so that it can predict turbulent kinetic energy from this knowledge. And yi is our response variable, that is turbulent kinetic energy, that's yr. Using xi, can we estimate yi? Right, that's our question. And a machine learning algorithm can grasp if there is some kind of relationship that this temperature can help to predict the turbulent kinetic energy. That means that is fire turbulence. And this is our objective function. This is our machine. Fx theta is our machine. Here, this machine, different kind of machine we have used. And this machine, we have to, machine can learn from the data. And we need to minimize the loss. There might be some error, right? During the learning process, there are trial, error, and they can find the best combination so that they can get the value out. This is our objective function. We have to minimize this loss, and this is our solution. This is totally mathematical modeling for machine learning algorithm. For all algorithm, this is the generic algorithm we got. Now, I have an in-depth analysis for everything on my paper, but here I just summarize what I have done for the machine learning deep neural network. These are the hyperparameters and parameters, because we have to tune what makes the best result, right? We have to get something down, something up, something down, something up, and get the trial that. And we need to input some math there. Is there some better result can we get? That's what we did. These are the parameters and hyperparameters during the training process. We have used like deep neural network, random forest regressor, k nearest neighborhood, Gaussian process regressor. These all are the parameters and hyperparameters. They are optimized using the mathematical insight, machine learning requirement, and our trial and error approach, our research. This is the optimized one. This gives the best result out of all under our research. That's the machine learning algorithm we have used. And the question is why we use TKE for our research. That's the one big questions. Why the TKE? The topics is we are analyzing wildfire turbulence and propagation and behavior. How can we study the behavior? That's the question. The behavior physical term we can do by using the TKE. It is turbulent kinetic energy. This is the physical term that says how the fire is behaving during the burn. That's why, what does it do? This is the key indicator for the turbulence, right? It quantifies the chaotic airflow from the wildfires. When there is a wildfire there, it quantifies, gives the number, right? How the fire is behaving. So that we can analyze mathematically, and machine can analyze. And fire atmospheric interaction. There is a lot of interaction between the atmosphere and fire, and that interaction is grasped by this TKE, and it influences fire spread, how fire is spreading, right? And this one is ember transport. Means suppose we have a wildfire and fire is transporting further. It depends on the fire turbulence. If you have a high turbulence, fire goes very fast. It transports to one place to other, like in California. We have seen there. They are the turbulence. That is important factor. That's why we chose TKE to get the behavior and propagation of fire during the burn. Now this is the first result we got, correlation between the turbulent kinetic energy and our predictor variable, that is temperature. T1, T2, T7 and our sonic. These are the temperature we have collected during the fire. And what is the relationship between temperature and turbulent kinetic energy? You can see here like let's say negative 0.25 here. This is the correlation between the T7. The T7 is the temperature measured from the 100 centimeter, 1 meter height from the fire. And the TK, turbulent kinetic energy, its correlation is negative 0.25. It's not much. It's not a good correlation, but they have at least some relationship. And we can see here, and here on the horizontal variable, we have a B1, B2, B3, B4. These are the data collection center. From the B1, we have collected the data. From that data, it shows this correlation, like T1 and TK has a relationship factor that is negative 0.19. That is the correlation coefficient between TK and T1. And it seems that the B4 truss, from the truss before this, it has a higher correlation than other. From here, the C1, C2, C3 trusses, it seems that the C3 gives the higher correlation than others. That's how we got from this. And that's the one Carl Pearson's, they made the correlation coefficient formula. That's the linear correlation coefficient, linearly it is correlated. And there is another one, Spearman's rank correlation coefficient. That is a monotonic correlation coefficient. That is not linear, but even though it covers the increasing, decreasing pattern, but it is not a linear correlation. This is a monotonic correlation. It depends on the rank of the values. And we got this like almost same result, right? Correlation very small here, but it is a bit better than the Pearson's correlation. And on the B4 set, we got high correlation here, 0.55 looks the highest one. It's not good even, because the correlation should be normally, it should be higher than 60, 70, 0.6, 60, 70% is better. But at least we got some correlation between the temperature and turbulence. This is the another data set C, the same pattern that we have got. But same here, on the C4 data, we got the higher correlation. And next, we got the correlation. We found the correlation between our predictor variables and our response variable TK. It's quite smaller. They are not much. They don't have much high relationship. But even though they don't have a high relationship, the machine learning algorithm we have tuned that graphs the correlation between them, and they found on the basis of temperature, we are successfully estimate the fire turbulence with respect to time. That's the result we have here. Now we trained the data. After the correlation analysis, we trained the data. We put the data into the machine. A lot of machine we used. And we found the accuracy, how accurately the machine estimated the fire turbulence with respect to the time. You can see here model deep neural network. This is one machine learning algorithm. It has accuracy 52% on the B1 data set. 52%. It doesn't look like good. This, but you can see here Gaussian process regressor. This is one machine that has a 93% B1, 92%, 92. It has almost more than 80% for all prediction. That's a good prediction. Same here, extreme gradient boosting. This one, this is for the testing. What we did, we separate the 20% data for our testing, 60% data for training to know the machine. We use 60% data. Machine learned from there, and we use the testing data. Does the machine knows our testing data or not? And they give the accuracy like this. 90% accurately they predicted from their knowledge, from our training. And here, this is the validation also, cross validation. We have to cross check the machine. Are they right or not, right? Having the cross check also, we got the consistent result. Those who have high accuracy, they have also high cross validation. That means our result is not bad, right? It's not 100% we can say, but more than 80%, more than 90% is good result we got. This is the one of the R square coefficient. This is the quality measurement, performance measurement. How does it measures? it measures the variation of the target variable with respect to the dependent variable, how the training data changing, that makes the variation determination. That's why this is the one of the very important or famous tools to check the quality of our model. Next one, prediction evaluation. How we evaluate the prediction. You can see here, this is it looks small, but these B1, B2, B3, these are the data set. Each data set has 4 machine learning algorithm. I have just extracted out of 6 or 7, I have extracted 4 of them. They give the higher result. You can see the blue one is the actual data, actual TKE, and the orange one is the predicted, our machine predicted one, TKE. You can see if the orange is higher, you can see more orange, that means high accuracy we have. You can see here the random, the last Gaussian process regressor has higher this orange color. That means we have a high accuracy. Then, and on the y-axis, this is the TKE, turbulent kinetic energy from 0 to 6. If you have a 6 TKE, that means there is a high turbulence on the fire. If there is a like 1 TKE, turbulent kinetic energy, fire is small. There is not much turbulence. That's how this predicts. It is good evaluation. Another one, kernel density estimation. This also measures how effective how our machine learning algorithm is, how it is performing, the performance measurement. That means our result, if it has a high variation, the flat curve, that means our performance the machine's performance is not good. If there is a peak around the 0, that means error is 0. You can see here, this figure here, residue, this is the error plot actually. If this is the high peak and near to 0, that means we have a less error. That means this machine Gaussian process regressor, this has a less error. This algorithm, this machine is, it's very effective out of all. Right? XGB also looks like good, but for other like here, random forest regression, it has high variation. That's not good estimation. This is from this measurement, from these tools, we got this. And this is next, the last performance analysis is mean square error. Right? Mean square error and mean absolute error. That is also error measurement. How big error does each machine produces. There are definitely some error because this is the estimation. This is not equal value we got. But error, it's a 3-dimensional. You can see the error here. GPR here, less error. This is the height is less. That means we got a less error. If height is up more, that is a high error. Less error. This also, somewhere we got a bit high error, but overall analysis, we can see that Gaussian process regressor and extreme gradient boosting, they have their error is less on different data set, B1, B2, B3, B4, B1, B2, B3, these are the data sets. All the data sets, somewhere there might be some up, but mostly the error is less. Mean square error, this is error analysis, and mean absolute error. I didn't go the math behind it, but there is definitely some maths, but this is the error evaluation we got. Now our conclusion now. We did thorough investigation for everything. What is our conclusion? Conclusion is, oh sorry. Even though there is a lower correlation coefficient, but we have seen that the correlation between turbulent kinetic energy and thermocouple temperature, that is across the different tosses, it is not a location dependent. It's not location dependent. We didn't find for particular location it has a more correlation. We can't say anything. It is location. Sorry, I think that's if you go back to go back to, we can go later, but it's a location means somewhere it is higher correlation, somewhere it is lower correlation. Like a B4 data set, it's all the way to corner site. We got the data from there. and there is a higher correlation. The trough, like from the left corner, it has a lower correlation. That's why it are location dependent. Next, although the direct correlation between our temperature data and TKE has a weak correlation, we found our machine learning algorithm was effective. And here are top 3 machine learning models. Hoffman summary, Gaussian process regressor. It has highest RE square, lowest error, and KD residual is tightly centered at 0. That's why this is the best one. Second one is extreme gradient boosting, and third one is K nearest neighborhood. These are the machines. They can determine the fire turbulence better with on the basis of temperature. And next, what is the real-time application of our research, right? That's the important part, right? And we estimated from the temperature only. We didn't measure the wind speeds. There might be a lot of wind speed. We take the wind speed out. Only use the temperature, right, from different height. Can we predict the fire turbulence? That's our research. And that it helps. With respect to the temperature, we can do the fire spread prediction, how fire spreads on the basis of temperatures. What's the temperature on particular place? And how the fire is spreading on that temperature. That we can do from here. And prescribed burn means it is a controlled fire management. Sometimes we need to make the fire to stop the fire somewhere. You might know that. To stop the fire, we have to make the fire from opposite side, right? And that is a controlled fire we do from the fire scientist. With this research also we can do. And AI-driven fire monitoring. Nowadays, everywhere there is artificial intelligence. And our research also kind of artificial intelligence we have applied. And that is helpful. And fire simulations and climate adaptation, they are important. Real-time application. And our future work, we have already, I have told that it is a 5 terabyte data. We have a high infrared image also, like millions of images we have. We have a location coordinates for each device. That's also important, where the device is mounted. And that might, if you use that variable as a one predictor also, our estimation might be better. That's our future work. And especially we have a little bit started about the infrared image. Can we detect the fire, right, by machine learning algorithm on the prescribed fire? Where we started doing that. This is our future work. And I did this is under NSF fellowship under the summer internship done by Oak Ridge. And data acquisition data was founded by US Department of Defense. This font data was collected from there. And I have a research collaborator, Dr. Nicholas Skronsky, and some other 3 US forest scientists, and my advisor, from my PhD advisor. They were the research collaborator. Any question? Thank you.
I have a question. So do you know which, the 3 different kinds of wind directions that you were looking at that contribute to the TKE, do you know which one contributes the largest? Or could you tease that out of your
Yeah, because of the mathematical formula, right? It's a TKE is 1/2 U prime square plus B prime square plus W prime square. That math says that which one has the largest. Because if U is large, then definitely that has a more contribution to determine the TKE.
What I'm saying is, I mean, see, so TKE doesn't give you that information. That's hidden just in this number.
Yes, right.
And so my question is will your data allow you to pick out which is the largest contributor to TKE?
No, our data doesn't do that, because we use TKE just to compute we use the U, W, and V just to compute the turbulent kinetic energy, TKE, and then we leave it. we didn't get back.
Right, okay.
But definitely your question is right, because the contribution of UVW might be worthwhile
I was just
to have.
wondering if the up-down contributes more to the turbulence or if the side-to-side.
Yeah, right.
That's what I was
Right. That might be then another future work to get back to the UVW, and does it have effect?
Right.
That's good.
And so then I have another question. Well, I have a bunch of questions, but it was very interesting. I have a lot of questions, and that's
Okay.
it was interesting. The other one is, so when you have this setup, which sort of, did you have a feel for which sensor was going to produce, was going to be best correlated with TKE? You see what I mean?
You mean the plot? Which plot?
No, I was thinking about, I mean, so, I'm sorry, let me ask it this way. The thermocouples, right? So you did one at 0, 5, 10, and
Yes.
then up.
Yes.
So, which do you think, did you have a feel before you went in for which thermocouple, which level was going to most appropriately,
Yeah,
or correct,
we
closely correlate with TKE?
Right, we are feeling at first, we are feeling like the device which is very closer to the fuel beds, that might have better correlation, right? It was the hypothesis for us. We are discussing about that, but that we didn't find that one, because later on, what we got the hypothesis was wrong, because we got the correlation between T6, that is from the 50-meter height. They got the higher correlation than from the T1.
And so is that because the turbulence induced by the fire takes some space to develop?
Yes, they take some space, because and it is changing from the fuel, the height of the fuel bed from the ground. Its temperature definitely higher than like 1 meter up, right? The temperature.
Right.
And there is a sonic temperature. If you go back to, if you look at the correlation between the temperature produced by the sound, the correlation between TK and sound, they have like a zero correlation.
Yeah,
right? But during our training process, I tried to exclude that one because they don't have correlation. I tried, but that didn't work well. When I exclude that, and our prediction accuracy is lower. That means even though they don't have a relationship, it seems, but that has a contribution to have the estimation.
Something else, right?
Right. There might be something else.
And you don't know which other variable it is correlated with?
No other one. Just what do you mean?
Doesn't that suggest that that's correlated to some of the other?
Yeah, we tried.
T7, you just don't know which one.
Yeah, we tried for like non-linear correlation for other algorithm, but due to some time constraint and some of them didn't work. That's why I stopped. We did just 2 correlationship, and there were like 35 born. 35 born were there. Out of 35, we just choose 1 born, that is born 20 data.
Right.
That's why we have a huge data to have analysis. Yeah. And the machine learning algorithm, it has not been used a lot on this kind of data. That's why we have a lot of space to have future research. Any other questions?
I have a non-mathematical question. It was really interesting. Does the Forest Service have labs in geographic areas? This was the east. Do they have a central? Do they have a west? Do they have, and does that imply then they have different forests and different forest characteristics? The fire characteristics might be different, say, between east and west?
Yeah, right. That's a good question, because this forest, the USDA Forest Service has different forests in different area, and this is located on New Jersey, New Lisbon. There is a pine forest, right, canopied forest, and it's not big. I went there during my research. I went there, and that's most of the fuel beds are pine needles are there, right, and it's not applied to the other place where the pine needles is not there, right? That's why this is I don't say that this is a universal to all the fire research, but this applied for the particular place.
Pine pitch adds to the
Yeah, but the United States,
Volatility.
most of the forest has pine.
Right.
Do you do it at different seasons?
No, they have done like, I think 2 seasons, from March 2018 to June 2019. That means 2 seasons. They have done 2 seasons. Spring to summer, I think.
So is there a conversion through the analytics part of this for time correlation for heat versus the transfer to gas in fire science for adding oxygen and the heat to get combustion? Is there a correlation in there?
Actually they didn't do that. They didn't add the oxygen manually. They didn't do that, right? Actually it is a natural, right? Whatever environment is there, that's natural. They didn't produce some external oxygen there. That's the forest. There is a land, and they didn't do anything in land. They didn't make the land smooth also. Whatever land, it might be slopey somewhere flat, and they make just to make put the instrument and make the fire with some fuel beds. They have put the fuel beds.
Sure.
The fuel beds is mostly pine needles and some dried grasses and some woody materials, light woody materials.
So what's the practical application of the research when it comes to wildfire?
Yeah, there are a lot of applications because the wildfire is affected by the ambient condition, right? What weather is there, what kind of like windy speeds, temperatures, that affects much on the wildfire spread. That's what the main objective is. What is the interaction between the environment and fire turbulence? What is the effect there? Natural turbulence environment. Yes, that's the important, because you can see there. It depends on the weather, how the fire spreads, and that's what they wanted to have a collection data. Is there any kind of relationship we can get? How the environment affect the fire propagation or fire behavior? That's the implication.
The questions on the errors, the percent data that you say you use 20% for simulation data?
Yes, we use 20% for testing purpose, and I think 16% for validation purpose, and 64% for.
So the 60% is from the simulation data or the experimental?
Sorry?
It's from the experimental data? You got it from?
It's from all of the data from experimental. That we take the 20% data out, right? And 60% data out for the validation, cross validation. And there is 64% data left. That data put into the machine. So that machine learns, right, from that data and gives the prediction for the unknown data. Unknown data is error. Yeah, we got the error. You can see the error here. It's not that much small, but from 0 to 0.8, the maximum height, right? We got the like error given by Gaussian process regressor. It's less than 0.2. It's around very near to 0. That's the error, right? And there are some algorithm, like you can see red one. It's a deep neural network we have used. It has a higher error. It's like a closer to 0.8. That's why we concluded that this algorithm is not useful. That's the error. And there are other measures also we did. You can see here, this is the Gaussian kernel density. Yeah, this is also error plot, residual plot. And those graphs which are very close to 0 and symmetrical and peak, that means it has a less error. The variation is less.
That allow you to identify which type of model is better fit for this type of data.
Yeah, but like the model is machine is like a black box, right? We can't go very deep to the machine, right? We have to tune the hyperparameters. There are some parameters we can tune and that's the research we did. That's why we use a lot of machines and which gives the best right? I don't say that this is the universally best, but under our research, this is the best.
What you do.
Yeah, yeah.
So do you have plans to recreate this, different altitudes in different parts of the country? To build?
Yeah, for that question, that's good question, but that's not under my control because the experiment has been done by the fire scientist. It's a USDA fire scientist, right? And they might have a plan to produce the data from different part, but I don't have information right now.
That would refine it and make
Yeah,
it much
still-
more usable.
I'm still working with them because some other data, I'm still in contact with them, and they told me that I might be going in summer sometimes to work with them, and if they have a brand new data. But still, we have a lot of data to get through it.
Sure.
Yeah.
So is the data set that you have used public?
It's a, I don't think all the data are public, right? Because USDA sent me the data, the 5 terabyte data drive, right, to my house because it's a remote job I did, and that's what I have now. And some of the data I found online, some of the data, but not all. It's not that much public.
Very interesting. Can I ask you what the altitude was and the time of year?
It's an instrument.
Yes, of the time, what season, what time of year, and what was the altitude?
Yeah, altitude. This altitude of the place where the experiment has been done.
Yes.
I don't have that result, but it is a there was, but I didn't include here. It's maybe some latitude or some longitude there. It's a New Jersey.
Oh, okay.
Right? New Lisbon. It's near to Philadelphia. It's like 1 hour drive from Philadelphia.
Okay.
Right? It's a slopey land, not flat. And the altitude here, the truss. When I went there, it's like more than twice of a man altitude.
The reason why I asked that is obviously the lower in altitude, the higher the barometric pressure, the higher the oxygen content.
Yes, yes.
The higher the altitude, lower the barometric pressure, lower the oxygen content, and all this comes into play. But
Yeah, right.
at least there's proof here that there's a meaning.
Yeah, these are the instrument on the different altitude they have set up.
Yeah.
Yeah, from the fuel bed.
Do they not have a wind speed on there?
Yeah, they have a wind speed because here, this is the sonic anemometer. This has been set for all the place here. A1, A2, A3, A4. All of them has one device, sonic anemometer, that captures the wind speed from east to west, north to south, and bottom to top. And it captures the sonic temperature also, temperature from the sound wave. It captures from each places.
Very good. Very precise.
Any more questions? Let's thank our speaker one more time.
Thank you. Thank you so much.
Please help yourself to the refreshments and continue the questioning about fires.
Relationship between sound and fire.
Yeah.
That's what he said.